Alright, so in this video we're going to analyze the buck-boost converter in terms of its conduction modes, ripples, and so on. And we'll look at some waveforms as well, as we have in the past for the other videos. And so if you're not familiar with, first of all, the buck-boost converter, I'll link that video in the description below so you can understand how we came to this topology. Now you might notice in that video that this capacitor here exists, and I haven't included that here in this case. The reason for that is because in this case I'm assuming that VDC is a fixed voltage source, whereas in the previous videos we were just assuming generic voltages that were being applied to the terminals of the converter, and so we have to include filtering in that case. In a case like this you don't need to, assuming it's a perfect DC source. So one key thing to highlight about this converter is the output voltage. You'll notice that the sign of the output voltage is flipped, and that's because we established again in that previous video that the voltage across the inductor, the average voltage across the inductor that is, over a full switching period has to be 0. So the average voltage across the inductor over the period has to be 0. Now that means one of these has to be negative. So either the input is negative or the output is negative. But rather than think about positive and negative, we should think about the same or the opposite polarity, because it might be that you have the input being a negative voltage, and so then the output ends up being a positive voltage. But whatever the case may be, is that the two have to be opposites. Now in this case, I'm assuming that the input is positive and the output is negative, just based on the way I've drawn it. I could have very well drawn it the other way and we would have ended up with the exact same relationships. But one thing we did establish last time was that we said that VO over VDC is going to equal D over 1 minus D. Now last time, or I guess in general, if you see a negative sign here, that just implies that they're inverting, or that this is an inverting sort of conversion ratio. But in this case, because I've flipped the sign of VO already, I'm already assuming that it's a negative voltage, so I don't need to include that here. Now, if you like to keep it the other way, then you like to have this positive at the top and negative at the bottom always, then you can do that as well, but then this has to be negative here in the equation to account for that. And of course, we know that IO over IDC is equal to the inverse of this thing here. So what we're going to do here is we're going to draw some waveforms, as we always do. And so if you imagine between 0 and dt that this transistor Q is conducting. If this transistor Q is conducting, then the diode here is going to be off. That means VL is going to equal VDC. And again, in this case, I'm assuming VDC is positive, so this will be drawn above 0. Okay, and so this we can obviously label as VDC. And then when the switch or the transistor turns off, the diode will be forced to turn on. And the diode turning on will connect VL to negative VO. And so then we can draw this being below 0, like so. And I mean, we should also, maybe I shouldn't draw it like that. Otherwise you might confuse whoever's watching this as they're the same magnitude. They're not the same magnitude, although they could be. But in this case, in the general case, they're not. And nor does it have to be larger or smaller. It could be one or the other. It doesn't have to be, in this case, like I've drawn smaller. But this is going to be minus VO, okay? That's what this thing here is. This is minus VO, and I'm putting brackets there so you don't confuse this with like a dash or something that I'm putting beside there. But this is minus VO. And if that's the case, and what I'm going to do is I'm going to draw this waveform such that it's the boundary between CCM and DCM, because the waveform for CCM and the waveform for the boundary is the exact same, but then we can discuss both cases with the single set of waveforms. So what we have here is you have this current increases rampwise, and this current here decreases rampwise like that. And here you'll have VDC over L, and here you'll have minus VO over L. So what can we do now with this? With this, we can say that this here is the ripple delta IL. And we know that the ripple, delta IL, is equal to the applied voltage, which in this case is VDC, over L, times the time that it is applied for, which is dt. Okay? Now this can also be written as VO 1 minus dt over L. And that's just using the conversion ratio that we have there just above. Now, during this time, you will also have an average, right? So this is going to be an average inductor current. And at the boundary, we call this average current ILB, because that's the boundary current. And based on this waveform, you can see that the average is going to be right in the middle, which is what the average is, but the average is going to be 1/2 of the ripple. So ILB is going to be 1/2 of delta IL. And that means it'll be VO 1 minus D T over 2L. So that's the ripple. That's the average inductor current, or the average boundary inductor current based on the ripple. That's what we meant to say. And so we can kind of highlight that because it's fairly important. And this you can use to determine, well, depending on what you choose to compare, you can use to determine whether the thing is operating in CCM or DCM. If you want to compare it with the output boundary current, IOB, if you want to determine that, I guess, from the circuit, we can look at the circuit here and we can establish that if this current here is IDC and this current here is IO, then this current here must be IL. Meaning, if I know these two currents, which I can relate them to one another based on the current conversion ratio, based on the voltage conversion ratio, then I can also determine what the boundary of either the input or the output is and I can use the boundary of the inductor current to do that. So if I want to do that, then I can say that IO equals IL minus IDC, right? And I can relate IDC to IO using the conversion ratio, meaning I can write an expression for IOB, and that is IOB equals VO 1 minus D squared T over 2L. And so this is IOB, whereas the other one was IOL. Okay? And so this is IOB. So if you want to determine the mode of operation, you can just compare this with IO directly and you can find out what mode you're operating in. Now, we can also go a little bit further and we can write what the maximum boundary currents are. And so the maximum boundary currents will be based on the actual equations of the currents themselves. So we see from ILB's equation that ILB max happens at D equals 0, because when D equals 0, this numerator is maximized. And so we can say that ILB max is going to be equal to VO T over 2L, and this is when D equals 0. And then you can say that IOB max, similarly, you can use the exact same approach, but use the IOB equation, and we can say IOB max will happen at the same time, and it will be the exact same expression, right? Because the two are the only difference between the two is the squared term, and since the D disappears, the result, I guess, wherever's left over, is the exact same. Okay, so based on these equations, then we can say that we can write ILB and IOB in terms of the maximums. So we can say that IOB is equal to IOB max times 1 minus D squared, and we can say that ILB is equal to ILB max times 1 minus D. So we have these two equations. Now, let's go into the DCM. So we have these equations, and then we're going to go into DCM given these two, having established these two relationships for the boundary. So if we look at DCM mode, again, we know that the inductor current will be 0 for some duration of the time, and that's sort of one of the key characteristics of DCM modes of operation, but the voltage waveform also changes slightly. And so we have VL and we'll have IL, and I'm going to assume that, let's do this for DT, let's say this is delta 1, and then maybe we can call this delta 2. Okay, so VL during the first part, so from 0 to DT, so let's say that this is DT, let's say that this is delta 1t, and let's say this is delta 2t, and that obviously this whole thing is t. I mean, that's kind of standard, I guess. In any case, this VL will be positive. It'll be VDC here, and then it'll drop down to minus VO there. But then what happens during delta 2 is that this goes to 0. And the reason it goes to 0 is because the inductor no longer has any current flowing through it. So then the inductor voltage is forced to 0. So this is VDC, this is I guess we can do this here. Now we can say minus VO. And so the inductor current during this time will rise up here like this, let's say, and then it will drop like this, and then it will stay at 0 for this time, and then it'll continue to go up again. And so during this times, obviously, I mean, we know that the ripple is still the same, so this is still VDC over L. This is still minus VO over L. But what we can establish from all of this is using the volt-second balance, we can say that the average voltage over the period needs to be 0. So you have VDC times dt. So you only have two parts to consider, really, right? You have this delta t, sorry, you have this dt, and then you have this delta 1t. So during the first part, it's VDC dt. Then it becomes minus VO times delta 1t, and that equals 0. So we establish that VO over VDC equals d over delta 1. And that means that IO over IDC is equal to delta 1 over d. And then, based on this, you can say that the average current, and how do I find the average? I'm going to say base times height divided by 2. It's going to be VDC over 2L dt d plus delta 1. And then you can take this equation, you can take these two equations we established, well, really one of them, you really only need the one on the left. You can take all of these equations, and then you can establish the following relationship for D, the duty ratio. This is VO over VDC, and this is IO over IOB max. And again, we're looking at the duty ratio here because in a practical setting, you would have a certain operating condition, and you would be trying to control D to provide a certain conversion ratio. So if in case of a power supply, let's say, you have a 5-volt power supply. So you want the output to always be 5 volts, regardless of what happens to the input. Now, what that means is you need to adjust the duty cycle. So you want a good model of the duty cycle. Now this is exactly what this expression here is it's a very concise expression for the duty ratio, which is exactly what would be useful in a practical setting. So the last thing we want to look at here is we want to look at the voltage ripple on the capacitor. And so to look at the voltage ripple on the capacitor, we're going to look at a slightly different approach than the one that we've done in the previous videos. And this one is going to look at the charging and discharging of the capacitor as a sort of, I guess you can, because you can integrate the waveform of a current, you can determine a charge or a net charge during that time. You basically want the charge in the capacitor to be 0, and we're going to establish that type of relationship here for this converter. And again, we're going to assume DCM mode of operation, or sorry, CCM mode of operation for this, because the models for the two are fairly close when it comes to the capacitor ripple, and so the CCM is easier to analyze, so we will go ahead with that. So I want to plot the diode current here, and I want to plot VC here. And the reason I'm plotting the diode current is because the diode is connected to the capacitor in this case, right? So this is the diode current now connecting to the capacitor, whereas in other converters it's different components. So in the buck converter, it's the inductor current, for instance. So in this case, it's the capacitor current. So what's going to happen during the time where the switch is, or the transistor is on, the diode current is 0. And then after it turns on, or after the switch turns, or the transistor, sorry, turns off, the diode turns on, meaning the diode current will increase, and then it follows the same shape as the inductor current, and then it'll go down to 0, and then it will go off like that. So we have here, during this thing, we can call this the average, okay? And the average of ID is equal to the average IO. And I know that because in this waveform here, there is no average current in the capacitor. So the entire average current of the diode has to be the average current of the output. Okay? And so that means in this case, any positive and negative sort of charge will be basically a result of anything that's above and below this waveform. Okay, so what you would have here is you would have maybe we'll use an orange. You have a delta Q during this time, and you have a delta Q during this time. And so basically, we're assuming that, again, we're assuming that the output is purely DC and that all of the ripple is in the capacitor. So we know from capacitor, I guess, physics, or the physics of capacitors, that the delta V, I guess C in this case, is equal to delta Q over C. And delta Q is the change in charge, right? And so in this case, what's causing the change in charge, it's going to be I/O times dt is what this area is at the bottom here, right? So I/O times dt is charging in one case and then discharging in the other case. So in this case, it's discharging from 0 to dt and then charging because it's above the average. So that'll be whatever the excess charge is, because overall we know the same way that the inductor has a volt-second balance, the capacitor has a capacitor charge balance. So that the current, it's basically the analogous thing for capacitors, but it's for the current. So the current has to be 0 over 1 switching cycle. And so what that tells us here in this case is that we end up with I/O times dt divided by C, because that's what delta Q in this case is equal to. That's what this area here is, for example. And so we know that I/O is VO over R, and this is dt over C. And so you can say that delta VO over VO is equal to dt over RC. And so this is a sort of different way of modeling this ripple. I mean, you can also, as we have in the other cases, you can also consider the current of the capacitor, and then sort of say IC equals C dV dt, and then you can have, what the capacitor current is during the second. Well, in the first part it's 0. During the second part, you know what this expression is. This is minus VO over L, and so you have that equation. You can plug that into the IC equals C dV dt equation, and then you can have some expression in terms of L's and C's, as we have in the boost converter video as well as the buck converter video, I think. And so there are multiple ways to actually model this ripple. This is just one such approach. So maybe as an exercise you can do that, and you'll find that the number you get at the end of the day is roughly the same. So in an equation like this, you can use the percent of ripple that you want relative to the maximum, or relative to the average, sorry, and you can calculate based on that what the value of C should be, for instance, or if you have a certain C, what kind of ripple you'll expect, and so on. And so again, this part during this time, we forgot to actually draw the capacitor voltage, which we can do now too, which is not a problem. So during the time between here, we said that as this is below this average, that means when it's below the average, it'll be discharging. When it's above the average, it'll be charging. That this will then be, again, discharging during this time, like so. And if it's discharging there, that means it must be charging here. And when capacitors charge, again, the current and the voltage of the capacitor are related through a sort of time derivative relationship, meaning if this is a ramp, then this has to be a sort of parabola, I guess you can say. And so that's what you have for this case. And this is obviously what we're calling delta V. Well, delta VO, I guess, or delta VC. I can say delta VO equals delta VC, just to be consistent with everything else. So what did we do here? We analyzed from the sort of top this buck boost converter, practically speaking, and we looked at how to develop the expression for the boundary current for both the inductor and the output, depending on which quantities you have. Usually you'll have the output, so it's good to have this output equation. Then we established a couple of relationships based on these two boundary currents. We saw that these two boundaries are maximized when D equals 0. And so based on that, you have these two relationships. We only ended up using one of them really for this duty ratio in DCM. And so in DCM, we saw that obviously the inductor current will be 0 for some substantial portion of the interval. And so that's what we call here delta 2. And during this, so based on this mode of operation, we've established based on the VSB, or the volt-second balance, that this is what the sort of conversion ratio should be. And then based on this relationship, as well as the fact that this average current here, this IL, should be equal to basically just this, the average of this, or the area under the curve of this part, which is the area of the triangle, which gives you this expression. Based on these two equations, as well as this IOB this IOB max here, we established this equation for the duty ratio. And then after that, we looked at the sort of capacitor dynamics of the whole situation, and we approached it slightly differently. So we said that the area under here, this is the time where the capacitor will be discharging, and this is the time where the capacitor will be charging, because it's greater than the average, because again, the average itself would not charge anything. So it has to be that the ripple is charging and discharging the capacitor, and it's the deviation from the average that would do that, because if you just supplied a capacitor with a constant current, it would not charge or discharge. It would only charge and discharge whenever you would be deviating from the average. So a positive deviation would obviously charge it, and a negative deviation in this case would discharge it. And so based on that sort of physics analysis type of approach, we've developed this expression here, which gives us this very clean and compact expression here for the output ripple of the buck boost converter. And again, this can be used for DCM and CCM, although the results for DCM will be slightly different. We analyzed here with the assumption of CCM, but the difference between the values that you get is usually negligible. So you can use the CCM equation for DCM operation. You might get some slightly different results if you were to practically implement it or put it into a simulation or something. But for the most part, I mean, it's fair to make that assumption. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.